So one of the uses of the model is to make predictions. Making predictions is very simple once you have the model. So suppose we have the second example, the one with the large, and we want to predict the average tree height of the large based on the mineral composition. We could say we have a nitrogen level of 1.9, we have a phosphor level of 0.2 and a potassium level of 0.7. What we then do is we just take the model, we take the coefficients and we plug in the values for the different predictors. If we do that, we get an average length for the tree of 163 centimeters. So it's just plugging in using the coefficients that we made. The question here, the real question is, how accurate is this prediction? So we have the model, we make a prediction, but is it also a good prediction? Is it a very accurate estimation of the true average length? For this, we have to take into account the variability in the model. So for predictions, there are two types of variability. On the one hand, you have the variability of the data points. So how are these spread around the regression line? Are they widely spread? Are they close by the line? Second is, how well did we estimate our model? So are the coefficients of the model itself accurately estimated? The first type of variability is easy to find because it's given in the output of the model. So when we ask for the summary of the model, we get a residual standard error, which basically gives you the variability around the line. Why? Because if you have a regression line, you have your observations, which determine the regression line. The spread of the points around the regression line is actually just given by the residual, so by the difference between the observation and the prediction. So the residual standard error will give you an idea of the variability around the line. So how are the data points spread around the line? The other part is then how well did we estimate them? So if we want to explain the variability or the residual standard deviation a bit, it basically tells us that 95% of all the lengths for given fixed values of the predictors will lie within a distance of 2 times this standard error, in our case 71.1, around the mean. Why the mean? It's the same as with the confidence interval. Also for the confidence interval, we had the confidence interval is the mean plus or minus approximately 2 times a standard error. Here also it's the mean because the model, we started from the assumption that our model was a model for y, or the average value of y given x. So we have again a mean. Around the mean, we can, similar to confidence intervals or to reference intervals, make an interval which is based on a quantile times the standard error. So the thing is, what we need here is a prediction interval. So it's an interval for the predictions, not for the observation itself. So a prediction interval has to combine both of the inaccuracies, so the inaccuracy in the data points and the inaccuracy in the model. What it tells you is that a prediction interval will have a random observation, so it will contain a random observation with 95% probability for given predictor values. So it is for fixed values of the x, of the different predictors. We know that with 95% probability, a random observation will lie in the prediction interval. So if we take 100 prediction intervals, so we would take 100 samples, 100 intervals. In 95 out of 100 cases, the prediction would be in the interval. It's very similar to reference intervals, except that a reference interval was for the observation, just a random observation. This is for a random observation with given predictor values, so with given x values. How do we make, on the one hand, the prediction, on the other hand, get the prediction interval in R? It's very easy. We use the function predict. So we take the model, we say for which data points we want to make a prediction, and then we say whether or not we want to have a confidence interval, a prediction interval, or no interval. So for the first example, the simple linear regression where we explain the basal area in function of the tree density, what we can do is, for example, make predictions for all values from 800 to 2200. So we say we have a riparian density, so a tree density going from 800 trees per kilometer to 2200 trees per kilometer. We put them in a data frame, so that's an important thing for the function predict. The new data that we want to predict have to be inserted in a data frame, otherwise the function won't work. And then we say we want to make predictions for these values, based on model 3, and then we do it once for the confidence interval and once for a prediction interval. So what we get is a fitted value, so this is my prediction, y hat, and then here we have a lower bound and an upper bound for, on the top of the screen, the confidence interval, on the bottom of the screen, the prediction interval. So what we immediately see is that prediction intervals are broader, they are wider than the confidence intervals, which is logical because they have two sources of inaccuracy, whereas the confidence interval only has the first source of inaccuracy. So confidence interval takes into account the variability of the data points, but there is no underlying model. So for the prediction, it will also look at the inaccuracy, the variability in the model, add it into the interval, and trivially, the interval will become wider. If we do it for the second example, we look at the largest. We have the specific values nitrogen, phosphor, and potassium. We plug them into a data frame. This data frame we put into the predict, and then we say we want to predict model 8 with the new data, and then again confidence interval or prediction interval. Same thing here, we get a fitted value. So this is my prediction, 163 centimeters as average height of the tree for this given mineral values. And then we have the confidence interval, which is smaller than the prediction interval. Another way to look at predictivity would be to compare the two types of variability. So variability around the regression line, the first type, and then the variability on the regression line, the second type. So the first type of variability is how are they spread around the line. The second type is what is the variability on the line. So basically, how much of the variability can we explain through the regression model? If we do that, and we illustrate this with this example, we get the following plot. So on the left hand, you have a scatter plot of the data. So in black are the data points, the observations. The blue line is the regression line through these observations. So y in function of x. And then the red line, these are the predictions, or the red dots are the predictions for the different observations. So every observation corresponds to one prediction. Something like that. What we then can do is we can look at both sources of variability. On the one hand, we had variability of the data points around the line. So what we can do is we can look at the difference between my observation and my prediction. So these are actually the residuals that we are looking at. So how far away is my observation from my prediction? And we get the type of variability. So we get here, the black dots in this case are all the residuals. And then the variability by the residuals, you can get an indication about how wide are they spread. On the other hand, if we want to look at what is the variability on the line, what we can do then is look at the difference between the predicted value and the average value. So what is the difference between my predicted value and the total average of all my data points? They are given here. So these are all those values. And again, variability is indicated by how wide they are spread. If we then look at specifically high predictivity, we get the following. When do we have high predictivity? We have high predictivity if there is a low variability around the line. So if basically all the black points and the red points are very close to each other. So if my prediction is very close to my observation. So we have a very good prediction, meaning that every residual is relatively small. If we then look at it, we get the left-hand plot. Residuals are all very small and very closely grouped together, whereas the variability on the line will be larger. So what we do here is we do not look at the actual values of the spread, but what we see is that the variability of the residuals, so the black ones, the y minus y hat, is very small with respect to the variability on the regression line, the y hat minus y bar. So in this case, variability around the line is small with respect to variability on the line. If there is low predictivity, it means that my data are spread all around the space, and so it was very difficult to find the best line. It also means that in this case the line will be more horizontally aligned, and so what we see if we look at this, we see that we can get very high residuals, and so here there is a very high variability in the residuals. Whereas on the other hand, the variability for the regression line is pretty small. So the variability of the regression line is very small with respect to the variability of the points around the line. So low predictivity means that the red dots are grouped closer together, or basically here the y hat minus y bar are close together with respect, or if we compare them to the difference between the prediction and the observation. So we want to use these observations, we want to use this split in two types of variability, and we will do it by looking at the sum of squares. So a sum of squares is just the difference between two values squared and then summed over all the observations. The total sum of squares is basically relative to the total variation. Why? Because if you remember, variation was also something like y minus y squared divided by n minus 1. So we just don't divide by our degrees of freedom. So we just take the denominator. The total sum of squares is the difference between our observations and the average. So it's the variability that we have in the data set with respect to the center. What we can do is we can plug in or interject the prediction. So we add and subtract it, doesn't matter, doesn't change anything. So 1 to n. And now we can split this up. So we get, if we do it like this, so we have this, we split it in this plus this, the first and the second one, gives us the following. So it gives us the squared of the first two terms, yi minus y at I squared, plus y hat I minus y bar squared, plus, of course, 2 times the product of both. So yi minus yi hat minus y bar, I is 1 to n. It can be proved that this one becomes 0 in the case of linear regression. So this term falls off, and we are only left with the y hat minus y bar and the yi minus yi hat. So what we get now here, these are just the residuals. And so this gives me a variation in the residuals, this second term. So it's the sum of squares of the residuals. And this, it looks at what is my prediction. So what is the point on the regression line? And it compares to the center. So this is the variability on the regression line. This is the variability around the regression line. So this is what we called before type 2 variability. And this is type 1 variability. And so what we see is that the total sum of squares is equal to the regression sum of squares and the residual sum of squares. With this in mind, we can now look at how predictive is the model. So basically, how much of the variability can be explained through the model. And to do that, we just look at how much of the total sum of squares is explained by the regression sum of squares. So we divide SS regression by SS total, and this tells us what is the proportion of the variability of the data that is captured by the model, so that is explained by the model with respect to the total variability. We call this R squared, which might ring a bell, because before, if we had a correlation between two variables x and y, we call this one R. In the case of simple linear regression, so we have only one predictor, they are the same. This correlation between x and y, if we square this, it is also x squared, and it corresponds to this x squared. So in the case of simple linear regression, the multiple correlation coefficient is just the correlation between x and y and the square of it. So this multiple correlation coefficient will say how well the predictivity of the model is, so how much of the variability is explained by the model. Since it is a proportion, it's always between 0 and 1, because here the regression or the total sum of squares is the regression sum of squares plus the residual sum of squares. So it can be at most equal to the total sum of squares, and at least it's 0. So we get a value r squared between 0 and 1, which gives us basically a percentage of how much is explained. If we then look at both of our examples, so we find a multiple r squared value in the output. So for the basal area in function of the tree density, we have a multiple r squared of 71.59%. So it means that the variability of the basal area is for 71.5% explained through the or by the tree density, so by the model. In the other example, in the multiple linear regression, we have 88.36%. So 88.36% of the variability of the average tree length is explained by its mineral composition. One final remark. As we said before, you have two goals. Either you want to make a model for prediction or you want to make a model for the biological influence. We only demand a high r squared if we use the model for prediction. Because in that case, we want to have accurate predictions. We want to be as accurately as possible. So we want to predict well and have a high variability or a high percentage of variability, which is explained by the model. If we do not use it for predictive values, the r squared doesn't really matter. At that time, what matters is to avoid confounding, as we said before, and so to include as many predictors as possible.